All right, so we're going to take a look at aquatic ecosystems, and the whole reason is that we're studying the kingdom Protista, and most protists live in freshwater ecosystems. So aquatic ecosystems in general, and this is referring to all aquatic ecosystems, whether they be freshwater or saltwater, are defined by their depth, their light levels, their flow rate, and some of them don't flow at all, and those are referred to as standing water ecosystems, like ponds and lakes, and water chemistry. And I just wanted to make sure you understood what is meant by water chemistry. So the salinity, referring to the amount of salt dissolved in the water, the temperature, the dissolved oxygen, which has a lot to do with that concept of eutrophication that we'll be looking at again here in our study of aquatic ecosystems, and the pH, which relates to the carbon dioxide that's being built up in our atmosphere that's causing climate change. It's also causing acidification, and it's not only causing acidification of the oceans. You may have heard of ocean acidification, but it's also causing the acidification of freshwater ecosystems. So that's a problem. So Earth only has about 2.5% fresh surface water, and of that, only about 1% is easily accessible. So, there have been wars, and there probably will be wars fought over access to fresh water, unfortunately. If we could find a way to desalinate seawater, and we do have a way to desalinate it, it's just that it's not easy, and it takes a long time, and it's not cheap. But if we could figure that out, we'd have plenty of water. Fairly obviously, flowing water ecosystems include streams and rivers. And the source of water for most streams and rivers is runoff, but there's also a scenario that you can think of in a mountainous region where snow builds up at the top of the mountain, and then in the spring the snow melts and streams are created, and the water comes flowing out of the mountains in these mountain streams. So that would be the source of water in that case. And of course there can be springs, where the water comes right out of the ground, and that could be the source of a flowing water ecosystem, a stream or a river. And of course the direction of flow is always downhill. If you ever find a flowing water stream or river that is flowing uphill, you better come find me and show it to me. So the primary selective pressure in these flowing water ecosystems is the rate of flow. How fast is the water flowing? And remember, selective pressure is referring to natural selection. So in other words, where organisms live and what part of the flowing aquatic ecosystem the organism is adapted to is dependent on how fast the water is flowing. So there are going to be different organisms that are adapted to fast flowing water as opposed to slow flowing water. The next thing is that as the water flows along a flowing water ecosystem, as it gets further away from its source, the flow rate tends to decrease, and the dissolved nutrients tend to increase. And again, don't always think that nutrients are a good thing. Usually you think of nutrients as a good thing, but too much nutrients or too many nutrients is not a good thing. Remember, that's when we get into the whole concept of eutrophication. That's basically what the term eutrophication even means, is an increase in nutrients. So in flowing water ecosystems, streams and rivers, there's terminology involved. And the first one is what's referred to as the channel. And it's basically the ditch that the water flows through. The water of a stream or river is flowing through its channel. Excuse me, I just breathed in a fruit fly and just about choked on it. I'm sure you're laughing right now. This other terminology refers to areas of the stream or river having to do with the rate of flow and what causes the rate of flow to change. So riffles and runs and pools. The primary difference between these has to do with two factors, the channel profile and how much meandering is going on. And that affects the flow rate. So when you look at riffles to pools, riffles tend to be more shallow or more narrow, whereas pools tend to be deeper or wider. And so if you think about it, as you go from shallow to deeper, or you go from narrow to wider, what you expect to see in the rate of flow of the water is that the water is going to slow down. So there's a decrease in the flow rate between riffles and pools, and then runs are somewhere in between. So that has to do with the profile of the channel, as we're seeing in these diagrams. As it becomes deeper, the water slows down, and as it becomes wider, the water also slows down. Meandering refers to the curves in a river, and not all rivers curve, or not all rivers curve along their entire length, but what we're looking at here are each curve is a meander. So these are meanders, and meanders tend to slow the flow rate of water also. So the more meandering there is in a river, the lower the rate of flow. There's this term up here that I almost completely covered up with text, riparian corridors. Riparian refers to the habitats, the specialized habitats that are along streams and rivers. So the surrounding habitat can be completely different. I mean, you can have a river running through a desert, for example, and so there'll be desert out here, but along the stream, there's a whole habitat that's has the benefit of having access to the water in the stream, and so there's a lush ecosystem that's created there that's completely different from the desert that surrounds it. And these habitats can be important because they act as buffer zones. So the water that's coming into the river, for example, the riparian habitat can include wetlands. So the water that's running off of a farmer's field, for example, is running through the riparian habitat and through the wetland that's part of the riparian habitat, and it removes nutrients from that water before it enters into the river. Therefore, those nutrients don't build up in the river, and they don't get carried downstream into a lake and build up in the lake. So this is something that can reduce eutrophication, which is a good thing. Now, the problem is that a lot of rivers that run through cities, for example, the riparian habitat has been removed. And you can find situations where there's concrete all the way up to the edge of the river as it runs through the middle of a city. So that poses a problem for the runoff into that river. It's flowing right off of concrete into the river, and there's nothing to remove any nutrients or pollutants that are in that water. So again, they act as a buffer zone to decrease nutrients before the water enters the river. So in the note guide, I posed the question, how natural is our Cuyahoga River? And it's a lot more natural now than it used to be, and a lot of effort has gone into making it, returning it more to its natural state. They're in the process of removing dams, for example, and also big change has taken place since, for example, the 1960s and 70s, when the river was much more polluted than it is now. So what impacts rivers? Human activity. What human activity impacts the river? Well, we got municipal and industrial sewage discharge. Municipal refers to cities. So sewage coming from cities and industries dumping their waste into rivers. There's also agricultural runoff. So farmers' fields, they're fertilizing their fields, and that's running off into the river, and pesticides are coming along with that water. And those can be acted upon by light, and other changes can take place. So that's what these terms photolysis and hydrolysis are referring to, changes in the compounds that might enter the water. But the Cuyahoga River running through the middle of Cleveland got so polluted and got so much oil buildup, a film of oil at the surface, that it ignited and burned. So I believe the last fire was in 1969, and from that point, people really realized that something had to be done to clean up the river. So there's also biodegradation, but not everything biodegrades, right? So a lot of what goes into the river might be broken down by bacteria and fungi and decomposers. That's biodegradation. But not everything biodegrades. So whatever goes into the river may biodegrade or not. And things can be transformed too. So, for example, light will change things, and Other compounds that are in the water will change compounds that enter the water, and that those transformations may turn them into something harmless, but it might also even change them into things that are harmful, more harmful. A lot of things that go into the river are going to dissolve in the water. If you'll recall, dissolving a solute in a solvent, that creates a solution. And so when things are dissolved in the water, they're going to be carried the furthest downstream. They'll probably make it all the way to the end of the river. If the river ends up in a lake, for example, like the Cuyahoga ends up in Lake Erie, that means anything dissolved in the Cuyahoga River is going to eventually end up in Lake Erie. Some things, though, can actually evaporate from the water. So, like, there are compounds in gasoline and oil that are volatile. Volatilization is basically just referring to the evaporation of these volatile compounds into the atmosphere. We also, they used to think that dilution was the solution, that just dumping all these pollutants into the water, there's so much water that it would just become diluted and it wouldn't hurt anything, and it would eventually be carried downstream and they wouldn't have to worry about it anymore. But dilution is not the solution. They discovered that the freshwater ecosystems, the river and Lake Erie, was not capable of just absorbing all these compounds, and everything was okay. What doesn't dissolve are particles that would be suspended in the water. And remember, suspensions, the particles that are suspended in suspensions only remain suspended when the water's moving. So the water, when it slows down, larger particles will come out of suspension and fall to the bottom and accumulate on the bottom until the water speeds up again. So say, for example, there's a rainstorm and a bunch of water runs into the river, and that increases the flow. So when the water speeds up again, it'll kick up what's on the bottom and pick up and resuspend those particles that have accumulated on the bottom. And some of those can be contaminants and pollutants. So that's a problem for people that live downstream. There are also filter feeders and bottom feeders that, like these clams, are filter feeding from the water, and in the process they can be building up compounds from the water in their tissues, and some of those compounds can be pollutants and toxins, and so that's referred to as, here in the diagram, as bioconcentration. But then those organisms that have bioconcentrated those pollutants or toxins might be eaten by other organisms that are eaten by other organisms. So say a fish is eaten by an eagle here, and the eagle then receives a high dose of whatever toxin or compound that originated in that filter feeder. The concentration of the toxin or the pollutant builds up as you go from trophic level to trophic level up through the food chain or the food web. That's called biomagnification. And eventually the top level predator receives a high dose of that toxin or pollutant. And so DDT is an example of the kind of pollutant that we're talking about. It doesn't biodegrade. And we used to use it as an insecticide. And so it was sprayed all over the place as an insecticide, and it was found that it doesn't biodegrade, and it was just building up in the tissues of species. And it eventually prevented eagles from being able to reproduce. So the eagle population really fell drastically, and they became endangered. And it was all the result of the DDT that was biomagnifying in their tissues. So that was a problem, and now DDT has been outlawed. You're not allowed to use it in the United States. My point here is kind of that even though the pollution is in the river, those pollutants can leave the river through the food chain or the food web, including ending up in us, unfortunately. So that was your crash course in flowing water ecology, flowing freshwater ecology. Here we're looking at standing freshwater ecology, and that's also known as lentic. Those ecosystems are known as lentic ecosystems. And we're talking about ponds and lakes, but the study of lakes is known as limnology. And again, I want to bring up this concept of eutrophication, because lakes are the things that, ponds too, become eutrophic over time. And so there what we call effluent tributaries, which are rivers or streams that feed into lakes. So that's what we're seeing down here in this lower diagram. This would be an effluent tributary of this lake, and it's bringing in whatever is in that river is being brought into the lake. And a lot of times there's little to no outflow from a lake, and so this lake, like so many lakes here in Ohio and all over the country, are man-made. And usually when a lake is man-made, it's made by building a dam in a river. So here, notice in the diagram, there's a dam, and that's restricting outflow from this lake. So whatever comes into the lake tends to build up in the lake and not flow out of the lake. And so what we're primarily concerned with here is the buildup of nutrients. And you can see in the diagram here that they've shown a bunch of green stuff in the water, and of course that's representing algae. So it's showing that algae is blooming. We have algal blooms, population explosions of algae in the lake, and that's an indication that this lake is eutrophic. It's got too many nutrients build up in it. That's what eutrophication is. So it's being caused by human activity. That's what they're trying to get across here in the rest of the diagram, showing the cities and factories and towns that are and farms, and everything's running off into the river and running off into the lake. That's cultural eutrophication, a change in the lake, an increase in nutrients causing problems, and those nutrients are coming from humans, our culture. Some of the terminology that goes along with the study of lakes, limnology, is the littoral zone here, and that's referring to around the edge of the lake where the water is shallow enough that enough light can penetrate to the bottom to support rooted plants. So basically the definition of the littoral zone is the zone around the lake that is shallow enough for rooted plants to grow. And along with the rooted plants, of course, there are going to be algal species, algae. And so there's high productivity. And remember, in ecology, when we talk about productivity, we're talking about photosynthesis. So there's a lot of photosynthesis going on in the littoral zone. From the inner edge of the littoral zone all the way out to the middle of the lake is referred to as the limnetic zone, or all the way across the lake to the far edge of the littoral zone. Basically, you can just think of this as the open water. The limnetic zone is the open water. And you can see that it's divided up into layers, or what we can also refer to as strata. So what we see happening in lakes, especially in temperate climates, is seasonal thermal stratification. Seasonal because this happens in the summer. The stratification happens in the summer when the water warms up. The thermal here is referring to water temperature, and the water warms up at the surface, and that separates from the water that's colder at the bottom. And this separation can become complete, where there is no mixing or anything being exchanged between the layer at the top and the layer at the bottom. Now, of course, these layers have names, and we'll come back to that in a minute. But we also have the air-water interface here. So across the air-water interface, gases can be exchanged. For example, oxygen can dissolve from the air into the water, and carbon dioxide can dissolve from the air into the water too. And again, that can cause acidification, because when you dissolve carbon dioxide in water, that produces carbonic acid, which lowers the pH, and that's more acidic. There's also the wind at the air-water interface that's important in mixing. So if we look over here at this diagram, the wind is creating mixing. It creates waves, but it is also mixing. But notice that the mixing is only in the top layer. That warm top layer is the only layer that is involved in the mixing. It's not reaching all the way down to the bottom. So that top layer is known as the epilimnion. And the epilimnion has a lot of characteristics that make it different from the hypolimnion down here. So what we're going to do is take a look at those characteristics in comparison. So in comparison, the water temperature in the epilimnion is high. So high temperature. In the diagram over here, it specifies 22 degrees Celsius. That's about 72 degrees. It's the lower 70s Fahrenheit. High light. And that's why they have this labeled here, the photic zone. There's a lot of light in the epilimnion, or that's the zone in which the light penetrates. There's a lot of mixing, high mixing, and again, that has to do with the wind. The wind will mix the epilimnion, the waters of the epilimnion. High oxygen, because of the gas exchange, the oxygen dissolves into the water and then the wind mixes it. Basically, the whole epilimnion has the same high oxygen concentration. So there's plenty of oxygen available due to the gas exchange from the air-water interface or across the air-water interface. High pH. Now, I just told you that carbon dioxide can dissolve into the water and decrease the pH, but in comparison to the hypolimnion, there's relatively higher pH in the epilimnion, but that can be changed by the carbon dioxide that will dissolve into the epilimnion across the air-water interface. And there's high productivity in the epilimnion. Now, we also see high productivity over here in the littoral zone, and that's because of all these rooted aquatic plants and algae. Well, what the heck is producing, carrying out photosynthesis in the epilimnion? Well, of course, that would be the algae, right? Phytoplankton. There's also zooplankton here. So both phytoplankton and zooplankton are in the water, suspended in the water, and the phytoplankton are photosynthetic, so there's a lot of productivity, a lot of photosynthesis taking place. And that's why we are studying aquatic ecosystems along with the kingdom Protista, because phytoplankton and some of the zooplankton are protists. Phytoplankton are algae, and some of the zooplankton are protozoa. There are also animals like crustaceans that make up the zooplankton, but that's the protist and aquatic ecology connection here. So because there's a lot of productivity, that means that it can support a lot of different species. So the last thing to note here about the epilimnion is high diversity. There are a lot of different species that live here, so think a large number of fish species in the epilimnion. So that brings us to the hypolimnion, and as you can imagine, everything's going to be pretty much the opposite in the hypolimnion. In other words, compared to the high temperature of the epilimnion, we've got low temperature in the hypolimnion, and over in the diagram here it specifies 4 degrees Celsius. That's about 40 degrees Fahrenheit. Low light, that's why it's referred to as the aphotic zone. If you put an A in front of anything in biology, it means the opposite of, or not, or no. So, aphotic, opposite of photic. Low mixing, because again, the wind mixing that's taking place in the epilimnion does not reach all the way down to the bottom, as we see in the diagram here. Low oxygen. Now, why would there be low oxygen? Well, it's partially because there's no mixing, but there must be something removing oxygen down here, and if you'll recall, that all is involved in the whole concept of eutrophication. Everything, all the phytoplankton up here and the zooplankton and the fish that die and even the rooted aquatic plants here, eventually all that organic material can end up at the bottom of the lake, and it's decomposing. And there are bacteria that are doing the decomposing, and they're carrying out aerobic cellular respiration, if you'll recall. And aerobic cellular respiration is aerobic because it uses oxygen. So decomposition, the high decomposition going on at the bottom of the lake, removes oxygen from the water. It also creates carbon dioxide and adds carbon dioxide to the water, and that decreases the pH. So compared to the epilimnion, the hypolimnion has low pH. It's more acidic. So obviously there's going to be low productivity here too. You can't photosynthesize in an aphotic environment, so there's very low productivity in the hypolimnion compared to the epilimnion. So because of that, and because this environment is not very inviting to living things, there's going to be relatively low diversity compared to the epilimnion. In between these two layers, the epilimnion and the hypolimnion, is the metalimnion. Meta means middle. And that's where we find what's referred to as the thermocline, the change in temperature from the epilimnion to the hypolimnion, the thermocline. And this can be very distinct and relatively thin. It's being shown relatively thick in this diagram, or wide, but it can be very thin You could be diving down here and swim down to the thermocline and basically stick your hand through it and feel the difference in the cold temperatures around your hand just by sticking your hand through the thermocline. So, and you can actually see it sometimes too, because there's particulate matter that might be in the water that makes the thermocline visible. But there can be a huge difference right across a very thin line. And again, the separation is pretty complete between the epilimnion and the hypolimnion. And that separation continues throughout the summer, as I mentioned, until the fall. And then in the fall, when it becomes cold enough, it causes the surface water to cool down. The epilimnion cools down, and when it gets to a certain point, when it gets cool enough that the water temperatures are close enough between the epilimnion and the hypolimnion, the thermocline breaks down basically, and the wind is able to then mix all the way to the bottom. And that's referred to as fall turnover. So that takes place in the fall, and it's the turnover of the water, the mixing of the water, so that it becomes basically uniform again. That's fall turnover. So that's your crash course in the study of lakes, the study of limnology. I wanted to show you this slide because it gets back to that idea of eutrophication again, cultural eutrophication. I just think it's a good diagram, and I think it makes it very clear, and I just wanted to hit it one more time to make sure that you understand that it's an important concept for you to understand. So on the left here we see an oligotrophic condition, and on the right a eutrophic condition. And again, eutrophic simply means an increase in nutrients. And that takes place over time. In any standing aquatic ecosystem, that's going to take place over time. And that process of changing from oligotrophic to eutrophic is known as eutrophication. Now that can happen naturally, so there's natural eutrophication. It's also known as lake succession. A change, remember, succession refers to a change in an ecosystem over time, and that's what's happening here. The ecosystem is changing over time. But in natural eutrophication, it's a very slow, gradual process where natural nutrients increase in the aquatic ecosystem. Eventually, nutrients build up and the ecosystem becomes eutrophic. Cultural eutrophication is when human activity accelerates the process by dumping sewage, for example, or runoff from farmers' fields, fertilizers from farmers' fields into an aquatic ecosystem. That is going to increase the buildup of nutrients in that ecosystem and cause all the things that we see in a eutrophic lake. So we see an increase in nutrient loads, which causes algal blooms, both macroalgae and microalgae. Remember, phytoplankton are the microalgae. That increases decomposition because the algae lives and it dies and it sinks to the bottom and it has to decompose. So that increases decomposition, which removes oxygen from the water. And we also see the buildup of toxins that some of these algae produce. And they're showing here in the diagram dinoflagellates. You may recognize those. And remember, dinoflagellates cause red tides, and they produce a toxin. So that's when you don't want to eat shellfish that may have eaten filter-fed off of dinoflagellates. And so there's a die-off from the reduction in oxygen and possibly the presence of toxins from the algae. We have a die-off, fish die-off. And so that's what they're showing with the X's here, all these species dying off because nothing can live down here at the bottom where there's no oxygen. So that's, again, one more time, the process of eutrophication. Finally, I wanted to show you, because it is in our own backyard, basically, Lake Erie, and apply some of these concepts to Lake Erie, since we're looking at limnology, and Lake Erie is a lake. So the Great Lakes, if you don't already know, were formed by glaciation. In other words, at the end of the last ice age, the glaciers receded and left behind basins in which there was water, and that water has persisted ever since. And those are the Great Lakes. So we're looking at the profile of the Great Lakes here, which is interesting to look at. And the thing that is most interesting to me is, compared to the other Great Lakes, just how shallow Lake Erie is. This little thing in the diagram is Lake Erie. So these colors around each lake represent the watersheds of the lake, and the watershed is the area around the lake where the water will flow into that lake. So in other words, when it rains in any of this area around Lake Superior, for example, that water from the rain is going to end up in Lake Superior, unless it evaporates, of course. So that's what watersheds are. So this is simply showing the watersheds around all the Great Lakes. It says here that the water eventually ends up in the St. Lawrence River and out into the Atlantic, and this profile shows that, because water flows downhill, right? So the Great Lakes are at higher elevation, and the water flows downhill into the St. Lawrence River and then out into the Atlantic Ocean. So all the lakes are connected. The water from Lake Superior and the other Great Lakes end up flowing into Lake Erie, and they bring all their nutrients into Lake Erie too, which is kind of a problem. So that increases the probability of eutrophication of Lake Erie. So the western basin seems to be in the most trouble of Lake Erie, and that's because it's the most shallow. If you look at the depths here, so because there's less volume of water, it is subject to greater eutrophication, and that's what's happening. And we've seen that, for example, Toledo can't remove its water, can't use the water from the western basin as its drinking water sometimes, certain summers, because the algal blooms of cyanobacteria, toxic cyanobacteria, are so great that there are too many toxins in the water, so they can't use it. So that's an example and the result of cultural eutrophication. And we see the same thing even in the central basin. There's a dead zone that forms in the central basin every summer, and it's because of the thermal stratification that we were just looking at on the previous slide. This whole area becomes what they call hypoxic, which means without oxygen. That's what it says right here, Lake Erie hypoxic dead zone. And this is from 2005, but it happens. It has happened other years too, where there's just no oxygen in that whole zone in the bottom of the middle basin of Lake Erie, and nothing can live there. It's a dead zone. So that's just a little bit about our own Lake Erie, and if you want to know more about it, I included the URL of the PDF that I found that gives a lot of information about Lake Erie. So check it out for yourself.